Hello everyone, this is Charles. Long time no see. Today I'm going to talk about chemistry, a subject that is intriguing and also sometimes bizarre at the same time. But I will start from the basic. I remember when I learned chemistry, there was one lesson when we talked about whether reactions will go spontaneously. The idea of a spontaneous reaction is that the reaction will go forward to produce products when there's no other external energy needed to put into the reaction. So it's a natural process. That's as far as what I learned. But when I learned a spontaneous reaction, I studied an equation that is called the Gibbs energy of a reaction. The change of it equals the change of enthalpy of a reaction minus the temperature, the absolute temperature times the entropy of the reaction, which is basically here. Let's start with the energy of the reaction. When I was learning IGCSE chemistry, my chemistry teacher told me that most of the reaction in this world is exothermic, which means the product has less heat content than the reactant, which means that for the exothermic reaction, heat is released from the system to its surroundings. But I think I question why most reactions are exothermics. Is that all the reaction favors exothermic pathway? Well, certainly not, because we can see there are many examples actually that endothermic reaction can be possible. So by simply stating the energy of a reaction is not evident enough to determine whether a reaction will be spontaneous or not. However, through some research, I found out the fundamental idea behind all the possible ways of a reaction, which is the second law of thermodynamics. The second law of thermodynamics is associated with a definition called entropy, which can be understood by saying a quantity associated with the randomness or a disorder. For example, solid has less entropy than liquids, which also has less entropy than gas. If you have 2 moles of gas, compared with 4 moles of gas, 4 moles of gas has more enthalpies. Now, the second law of thermodynamics, which is a brilliant idea, suggests that in a spontaneous process, the enthalpy of the universe increases. We can treat this as somehow a truth behind all the building of chemistry reaction. And also, the enthalpy change of a universe is considered the sum of enthalpy change of the surroundings plus the enthalpy change of the system. Anything that is apart from the products, the reactant, is called the surroundings. This includes your solvents, your test tubes, your thermometers, and the air. So they are all surroundings. Congratulations! You now understand the fundamental truth of every reaction, but not yet. You still have to know some very important message in case you get wrong. Notice I highlight 2 key words in this statement. First is spontaneous, which means the reaction can go by itself. Well, another more important word is universe, which means the enthalpy change of a universe constitutes 2 things: the enthalpy change of a system and also the enthalpy change of the surrounding. You can easily find the enthalpy change of a system from any data booklet, but you might not easily find the enthalpy change of a surrounding. How do we relate the enthalpy change of a surrounding with some common nature of a reaction? Well, I will provide you the answer, which is for an object to absorb heat, its enthalpy change will increase. Why is that? Because the molecule will move more rapidly as the molecules are absorbing heat. They are absorbing kinetic energy. Particles that move slowly will have a, a less randomness, but for particles that move rapidly and colliding with each other, the enthalpy will definitely be larger. So, in the exothermic process, the heat energy of the system will gives out, release to the surrounding. So the enthalpy change of the surrounding will increase. But for an endothermic reaction, it is the reverse. The system will take in the energy from the surrounding. So the enthalpy of the surrounding will actually decrease. Now let's consider an example. Water, liquid water, will freeze to solid ice when the temperature is lower than 0 Celsius. But if we look carefully, we can see that this kind of physical reaction, also it can be regarded as a chemical reaction, is actually decreased in enthalpy because water is liquid and solid ice is solid. Well, there is definitely a decrease in the enthalpy of the system. But the reaction is actually exothermic. So the enthalpy of the surrounding will increase. This will compromise the enthalpy decrease of a system, making the enthalpy of the universe increase. So this, according to the second law of thermodynamics, the reaction is actually spontaneous. However, you may realize that ice only from ice, water only from ice, when the temperature is sufficiently low. It will be really strange if you start looking at your water at room temperature to stick to each other and expand and becoming crystals. Well, why is that? If this scenario is true, according to my eyes, there must be a link between the absolute temperature of the surrounding, which is also the temperature of the system, with enthalpy. Well, here's the link. Supplying heat to two objects, let's imagine. A, the object is higher in temperature. The particles are colliding faster. And B, the object, the same amount of object, the same material, but it has a lower temperature. Now we supply the same amount of heat into two objects. Which enthalpy will increase larger? Well, according to some common sense, I guess, the hotter object will have a smaller increase in enthalpy than the colder object. So some genius, I guess, find out an equation that relates the two quantities, which is the enthalpy change of the surrounding equals the heat absorbed by the surrounding divided by, which means ratio, by absolute temperature of the surroundings. Well, so this equation somehow gives you how to calculate the enthalpy change of the surrounding just by looking at the heat content absorbed and also the absolute temperature that can actually be measured. And from this equation, we can also see the enthalpy change has a unit of joules per Kelvin. Normally, when we look at per amount of substance, we'll add a per mole. So the enthalpy change of the surrounding can be altered simply by changing the temperature of the surrounding. The lower the temperature, the greater the enthalpy change. The higher the temperature, the smaller the enthalpy change. Now, as I mentioned earlier, the enthalpy change of a system can be obtained from data booklet. And now the enthalpy change of a surrounding can be calculated by temperature and the heat content absorbed. If we add the two, we can calculate the enthalpy change of the universe. Thereby, we can determine whether this reaction will be spontaneous or not. Bear in mind that the heat content absorbed by the surrounding is actually the heat content released by the system. The two things are, comprehensive. Like, if we put A into B, B must have the same amount of substance from A. So actually, you can always think there's two things in the universe: the system and the surrounding. The heat goes out must be absorbed by another person, another thing. Okay. Oh my god, I already made this video into 10 minutes or something, but I will make it quick. Now I have to tell you something more, just to give you a short ride, just to give you a safe ride. So now for an exothermic and endothermic reaction, we might realize, according to all the things I mentioned before, if we decrease the entropy of a system, the process must be exothermic. If we increase the entropy of a system, the process can be either exothermic or endothermic. If it's exothermic, it's always spontaneous, because the entropy of the universe will always be positive. But if it's endothermic, the temperature of the surrounding affects the magnitude of the entropy change of the surroundings. So when there's lower temperature, there will be some spontaneous reactions. What I've been talking about is all about entropy and temperature and exothermic and endothermic. I never come across with the word Gibbs energy. Well, what is Gibbs free energy? Actually, Gibbs energy is just an energy that invented by us for making our life easier. Gibbs energy can be calculated from the properties of the system alone. We converted all the properties of the surroundings into solely the system. Well, if you want to see proof, it's here. And the enthalpy change of the universe equals to the minus, the negative of the change of Gibbs energy of the system ratio over to the temperature of the system. So the Gibbs energy is inverse of the enthalpy of the universe. When the enthalpy of the universe is positive, the reaction is spontaneous, which means that if the Gibbs free energy is negative, the reaction is spontaneous. Bear in mind that Gibbs free energy does not equal to energy. So you cannot just say, oh, I realize the driving force behind all the great reactions, which is lowering the energy. No, lowering the Gibbs free energy, which is increasing the enthalpy of the whole universe. That's all I'm going to mention, explain, and talked about in this video. If you like this video and if you want to hear more about chemistry, just leave a comment or thumbs up. And I think I know all the subscribers, so please watch this video. And if you if you're not interested in chemistry, I hope this video doesn't freak you out. And what I'm going to say is, oh, by the way, I think the truth behind all the reaction, as far as I study now, is the second law of thermodynamics. But I consider the second law of thermodynamics as a truth, as somehow how the world works. But if you can tell me why the second law of thermodynamics actually works, you'll be very grateful. You can leave a comment below so I can study from you. And I think that's all I'm going to say, and bye bye.